Okay, so the last talk in the session is going to be a presentation of the ICAPS 2013 Best Student Paper called Trial-Based Heuristic Tree Search for Finite Horizon MDPs by Thomas Keller and Malte Helmert, and is going to be presented by Thomas.
Thank you, Andre. Okay, so let me quickly say a few words about the background of this work. We're dealing with finite horizon MDPs. Probably most of you know what finite horizon MDPs are. Important for this talk is that we consider MDPs with a huge state space. We have actions that have potentially very many outcomes. In our evaluation later, we will have a domain where the whole state space is actually the outcome of a single action. We are interested in planning problems, so transition and reward function are given in a declarative model to the planner. It can use the transition probabilities. And because of the huge state space, we will not compute complete policies, but we will alternate planning and execution. So we will plan for a single step, we will execute that step, we will get a successor state, and we will go on until the horizon is reached. Okay, we started this work by looking at algorithms that are currently used for MDPs, and there are lots of them. These are three that are quite popular, I would say. The first is AO star, which is just an extension of the A-star algorithm to non-deterministic planning. The second is RTDP, a dynamic programming approach. There are many variants of RTDP. And the third one is the quite popular UCT algorithm, which is a Monte Carlo tree search method. And we actually started this work by trying to analyze these algorithms and think about what do they have in common and where do they differ. And what we basically came up with is this quite simple algorithmic framework to the right, which shows a framework where all of these algorithms can be modeled in. And they are modeled as a trial-based algorithm, so an anytime algorithm that performs trials until a timeout is reached or until the MDP has been solved. And after the timeout is reached, the most promising action is returned. And initially, the tree that is built consists only of a root node that represents the initial state. And in the trials, we add nodes, alternating decision and chance nodes to the explicit tree, where decision nodes represent nodes that contain state value estimates, and chance nodes contain action value estimates. I will not go into too much detail regarding the framework, but all these algorithms basically go through three alternating phases. One phase where successor nodes are selected, a phase where nodes are added to the tree, and a phase where the nodes in the tree are updated with the new information that was gathered in the trial. And the algorithms can actually be described by only these 5 ingredients. There is an action selection. That means in a decision node, which of the chance nodes that are the successors of this decision node will I choose to simulate? Outcome selection is the same for chance nodes. The trial length is used to determine when to finish the trial, the current trial, when to enter the backup phase. And we have a heuristic function and a backup function. Okay, I will present this in a small example. So suppose this tree, this is the explicit tree after a single trial. There was a single trial over A1. And the rectangular nodes are decision nodes. The circled nodes are chance nodes. In the initial state, we have 2 actions. an action A1, which yields an immediate reward of 2, and an action A2 that yields an immediate reward of 3. And our current action value estimates for A1 is basically 15 plus the 2 it yields immediately, and for A2 it's 25 plus the 3 it yields immediately. So in this case, I will show it at the example of RTDP. At first, it needs to select an action. It must choose A1 or A2, which one will it simulate. And RTDP always chooses the greedy action. So in this case, it will choose A2 and end up here. Now we are in a chance node where it's supposed to select one of the outcomes. In the case of RTDP, this is done by simply rolling a dice and looking where we end up. So let's say it ends up here. And now we are in a node which does not have any successors, so it is necessary to add new nodes to the explicit tree by expanding the node and initializing the successors with a heuristic estimate. So something like this might happen. And what is happening now is that we are actually more or less in the same situation as we have been in the beginning in the root node. We are currently in a decision node. We have successor nodes which all contain estimates, so we can simply switch back to the action selection, or we can choose to say, well, we found enough information, we finish the trial and start to propagate. In the case of RTDP, this is not the case. It will go on until it reaches a goal state, which in finite horizon MDPs is all those states where the remaining steps are 0. So it will again go on, choose an action, choose an outcome, and so on, until it reaches a goal state, which is the moment when the backup function comes in. So let's say a value of an accumulated reward of 5 is propagated back in this part that is missing in this tree. So basically in every node it will start to compute a new estimate based on the successor nodes. So in the case of RTDP, it will use full Bellman backups. So in this case, it will apply a value of the probability weighted outcomes to a chance node, and it will maximize over its children. So in this case, it will now choose A4, which yields a reward of 8 plus 2, rather than A2, which only yields a reward of 8. And it goes on until the root node has been backed up, and this is the moment when the trial is finished, when it's checked, is it solved, or do we still have time for another trial, can we go on? Okay, so this was just one of the algorithms that can be modeled with this framework, and now I will talk a bit about how these three algorithms actually implement the 5 ingredients. And I will not talk too much about action selection here. It's a quite hot topic, I would say. There are many, many different algorithms that use different action selection strategies. Here, RTDP and AO star are greedy algorithms, and UCT has some way of balancing exploration and exploitation. I'm always not talking too much about outcome selection. Actually, there are not so many. Well, actually, I only know anytime AO star is the only algorithm that actually does something different from sampling here. So there's actually quite little research about choosing which successor to sample. Well, no, sampling is the only way that is usually done. Okay, in the algorithms we consider here, there are basically 2 possibilities to implement a trial length limitation. RTDP and UCT, at least the kind of UCT we consider here, there are different implementations of UCT, only finish when a goal state is reached, while AO star has a more global search behavior as it always enters the backup phase whenever new information is in the tree. That means whenever a node is expanded, it propagates the novel information up to the root. And our experiments showed that at least in some domains, this might be quite a good idea, because propagating the information back leads to more trials, and it leads to a situation where more time can be spent to look at the states that are quite close to the root, because states that are far from the root, there's only little probability that we will really end up in those roads. So it doesn't make sense to spend too much computational time far from the root node. The last two ingredients are the backup and heuristic function, where RTDP and AO star work identically. They both use full Bellman backups, which has the severe drawback that all outcomes must be explicated in the tree in order to be able to compute the backup function, which, as I said earlier, is a problem because there might be very many outcomes. They both need an admissible heuristic, and combined, this allows a self-labeling procedure which enables pruning and also termination once the root node has been solved. It's not necessary to go on with the trials when we know that we already have the correct state value estimate in our root node. UCT, on the other hand, uses Monte Carlo backups, where the current estimate is extended is an average over all trials that visited that state or that state action node. And it has the advantage that it allows the usage of non-admissible heuristics, which are often cheaper to compute and or are more informative. And also it does not have the drawback that it needs all the outcomes. It's fine if there's only a single outcome in the explicit tree, which is always the case because one outcome is chosen, and that outcome will, of course, also be there when the backup function is called. Okay, so that is basically about the framework, and now we started to think about what can we do with this framework. And we decided to simply look at the algorithms I just presented and see if there are some ingredients that are more desirable than others, and if we maybe somehow can mix them to derive better algorithms. So the ingredients that are in our setting desirable are again here. It's first the self-labeling procedure by RTDP and AO star. Then it's the limited trial length, the global search behavior of AO star, and the fact that we need only non-admissible heuristics and a single outcome for backup computation by UCT. So what we did is we basically said, okay, let's just start with UCT. We are not interested in action selection. We leave the heuristic as it is. So we start with UCT and we try to adapt the algorithm and to change some things in order to get the other two desirable ingredients as well. And the first algorithm we came up with is called DP-UCT. And it is basically a hybrid version of RTDP and UCT. But we could not simply take full Bellman backups and put them into UCT. One could do that, but the problem with that is then we still need all the outcomes that are we need all the outcomes to be explicated in the tree. So what we did instead is we extended it by a partial Bellman backup function where the state value backup is exactly the same as in full Bellman. That means rather than averaging over all successor nodes, we simply take the maximum, the best action, and in the chance nodes, we extrapolate the missing outcomes. So we basically pretend that what we have already seen is what probably will be in the other outcomes as well. The second algorithm is built on top of DP-UCT, so it has the same changes as I presented right now, but it additionally simply stops the trial whenever new information is available. So this is basically only a very, very small adaptation. and yeah, we can more or less regard it as a hybrid version of UCT and AO star. Okay, so now to the experiments with these algorithms. The setup is more or less the same as in IPPC 2011. We have 8 domains with 10 instances. We average the results of 100 runs. The horizon is always 40. And all algorithms use the same inadmissible heuristic of the Prost planner. And we also made experiments with a different time per decision, which ranges from something 0.015 seconds to 2 seconds. Okay, and these are the results in terms of IPPC score with the 2-second versions. So we compared our new algorithms with a basic UCT implementation, which is basically identical to the Prost planner, except that the Prost planner has an additional limited trial length. It always only considers a horizon of 15. That was basically the only difference between UCT and Prost. And I think, yeah, it's quite obvious that it worked a lot better. I mean, if you look at DPUCT, it's already an improvement of 0.04 points over UCT and over Prost more or less as well. And it is especially better in the domains where solving the root state is possible. This is mostly the navigation domain. I will show some more to that on the next slide. And at the UCT star, you can see that it really pays off to focus the search on states that are quite close to the root. The only domain where it did not improve, by the way, is the reckon domain. We also performed some experiments without a heuristic guidance, and it turned out that UCT star is more or less equally good on the reckon domain with or without a heuristic. So we believe that that it needs the heuristic more than the UCT algorithm. It needs the guidance more, and think that this is the reason that it did get worse actually in that domain. Okay, this is basically a graphic that shows how many states, how early during a run did we manage to label the root node as solved. And the highest possible value is 40. This is an average over all 10 domains and over all the 100 runs. And you can see that the navigation domain, for example, is almost always solved immediately in the root state. But also a lot of other domains are solved over the course of the run. It must not be the very first step, but for example in skill teaching, like after half of the run, it will start to produce optimal policies. And another advantage of this is obviously that we also save time because of the solved root state. As soon as we have solved the state, we don't need to spend the whole 2 seconds, so we can simply return the optimal action. And yeah, in some domains this pays off a lot, like in navigation it only needs 20% of the time. But yeah, overall in total it's only like 75% of the time that UCT star and about 80% of the time that DPUCT needs compared to UCT and Prost. And this is the last slide on the experiments where we alternated the time per decision in seconds. So on the left we have the 2 to the power of minus 6 seconds per decision. To the right we have 2 seconds, so the right basically is equivalent to the table I showed first. And it's again the IPPC score. And yeah, one can see that the anytime behavior of all algorithms is always the same. From the lowest time per decision, a UCT star is already quite far ahead, and yeah, more or less all of these lines are in parallel to each other. And what might be quite interesting is the fact that the Prost planner with 2 seconds performs about as good as the UCT star algorithm with something like 0.1 seconds. So it's also like 20 times faster to come up with equivalent policies. Okay, so to summarize, we described the trial-based heuristic tree search framework for finite horizon MDPs. We showed how algorithms can be modeled within this framework by only describing 5 ingredients, and applied the framework to derive novel algorithms by only mixing existing techniques. And in the end, we came up with the 2 algorithms which outperform the winner of IPPC 2011 on the domains of IPPC 2011. Thank you.